This is another simple truss example problem. Again, I call it kind of an easy truss. What makes it easy, and then this is a tower truss, and it's got several loads pulling to the right off of this right-hand chord of the truss. And again, one of the things that makes this truss easy is that this left-hand chord is parallel to the right-hand chord. And so once we cut a free body diagram, especially in this section, the diagonal is the only member that has a horizontal component. And so it just makes it a little bit easier to solve. Again, this is like a typical exam truss question in that it asks you to find forces in DE and EF, which suggest analyzing the joint at E. And it also asks you to find forces in BC, BG, and GH, which suggests sections, the method of sections. Again, the exam doesn't tell you, okay, use method of joints or use method of sections, but you need to understand that that's what you need to do. Another thing to think about as you're looking at this truss before you even start working is these right-hand directed loads basically cause this entire truss to bend slightly to the right. And in that, with that kind of loading, basically all of the left-hand side of this truss and this top guy will all be in tension, and all of these guys will be in compression because of that. Finally, actually this member down here, AI, is a zero force. This is a right angle corner at a roller rule down here. If you look at the jointed eye, this guy's technically a zero force. Now he's needed because this member HI will slip off this roller without him. And so he's needed to keep this guy on the roller. But technically he develops no force because if you analyze this joint, there's no IX support force and there's no load there. So technically develops zero load. So let's start with joint E and let's analyze joint E. And again, I'm going to draw a free body diagram for you. And so at joint E, we have the joint itself. We have the force, which is 6 kilonewtons. We have the member coming down, and we have the member coming out here at a 3-4-5 slope. And this is F, EF, and this is F, DE. Notice again, I drew these as dashed lines. I didn't put the arrows on yet. Remember, these forces that act in these truss members these truss members are two force members, which means that the force developed in the members acts along the member itself. So every member that you see gives you a force direction or line of action. So the line of action of EF is vertical. The line of action of DE is at a 3-4-5 slope. But again, those forces can either push on this pin at E or they can pull. And so if you look at this guy and think about X and Y directions, it's pretty clear that FDE is going to have to pull to balance this guy in the X direction. Once you establish FDE, then you can think in terms of vertical. The load itself is only horizontal, but this member here has a downward directed force. And so this guy is actually going to have to act upward to ensure that E is in equilibrium in the Y direction. So the way we drew DE pulling on E, this guy is in tension because he's pulling on E. And this guy is pushing on E. And so that basically is assuming he's compression. And that agrees with what we expected from this tower. This whole side here in tension and this whole side here in compression. which is basically what we see here. Does that make sense? So once we've drawn that free body diagram, we can just write x and y equations at that joint. Remember, because this is a particle in 2D, we can write two equilibrium equations so we can solve for two unknowns. So in the x direction, if we take to the right to be positive, we have 6 minus 4/5 FDE is equal to 0. So FDE is equal to 7.5 kilonewtons. This number comes up positive, which means the way we drew it is correct, which is tension. In the vertical direction, we've got FEF minus 3/5 of FDE. And we can plug in 7.5 there, and FEF is 4.5 kilonewtons compression, which is the way we drew it. So that's that joint. And now for the section, to find these forces down here, that suggests a section. And so, again, you can take your paper and lay it on, if this is on an exam, you could bring a card in or whatever, and rather than redrawing this guy, you could just extend these forces down like this. This is up, and this is going to act this way for reasons that I'll explain to you in a moment. And so you could actually draw a free body diagram this way if you wish, and or you can redraw it the way I drew it here. Let's redraw it, so I'll just show you how to draw this guy. So what I would do is I would draw this square first. And so you've got that square, which is 3 by 4. And then I would draw that upper triangle, which looks like that. Then I've got a 6 and 8, a 10. We already decided that this end over here is in tension, and so this is FBC. We already decided this side is in compression, so this is FGH. And so now we need to draw this internal member here. And again, we'll draw this diagonal. So this is where this side being parallel to this side comes in handy. Because now when you think in terms of analyzing this guy in the X and the Y directions, all of these loads act in the X direction. This guy's vertical. This guy's parallel to this guy, also vertical. And so the only unknown that has an X component is this guy. And because all the loads are going to the right, then this guy is going to have to act this way to the left. So his X component to the left is exactly equal to the sum of these guys to the right. And so this is a 3, 4, 5 slope. He's F, B, G. Let's dimension this guy. I'm actually going to extend these to this point too, which is B. This is 3 meters, 3 meters, 3 meters, 3 meters. And then, of course, this is 4 meters here, 4. This is how I would draw the free body diagram and how you would intuit the direction of FBG. So now we can, because this is method of sections, which has dimensionality to it, we can write 3 equations to find our 3 unknowns. So again, because this guy's parallel to this guy, if we sum forces in the X direction, the only unknown with an X component is this guy. And then you have these forces. So if we take to the right to be positive, we have 6 plus 8 plus 10 minus 4/5 of FBG. And so FBG is 24 divided by 0.8, which is 30 kilonewtons. We drew it in tension, it came up positive, and so it's in tension. To get these other twos, we have to write a moment equation, and we'll write a moment equation about G, because there's 2 unknowns here. If I sum moments there, then the only unknown in that equation is going to be FBC. If I take clockwise to be positive, and summing moments about G, I have 6 times 6 plus 8 times 3 minus FBC times 4. And that's that equation. And FBC turns out to be 15 kilonewtons tension. Finally, to get FGH, I'll write 2 different equations to get him. And I think for most of us, just to sum forces in the y direction is probably easiest. So let's do that first. And so if we take up to be positive, we have FGH minus FBC minus 3/5 of FBG. And we get FGH is equal to 33 kilonewtons. And we drew it compression, and it came out positive, and so it's in compression. Another way to get FGH is we can sum moments about B. So B's not on the truss, but that's okay, that's permissible. We basically can slide FBC along his line of action. We can slide FBG along its line of action. They intersect at this point B. If I sum moments about point B, then around that point, I just have the 6 times 9, I have the 8 times 6, I have the 10 times 3, and I have FGH times 4. And so if you write those terms, plus, 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 minus FGH times 4, and you get FGH is 33 kilonewtons, and compression as well, which agrees with what we got here. So you should know how to write all of those equations. Again, this is a relatively simple example with relatively simple numbers, but it illustrates the process of a standard exam question of a joint and a section